Hello, this is the MA 16010 Spring 2025 exam number 1. So, first, let's start off with question 1. Question 1 says, find the following limit numerically. So, first, before we start this question, let's just quickly go over what a limit is. So, if we have some kind of function, a limit basically describes the behavior of the function. So in this case, for our function e to the power x minus 1 divided by x, since the limit is going to x equals 0, we're going to be asking, like, approximately where is the function when x approaches 0? And in this case, the reason we use limits is because if we just plug in 0, we get e to the power of 0 minus 1 divided by 0, and dividing by 0 is not allowed. So the default is plug your value in. If that works, then you're good to go. But if that doesn't work, we need different methods, and so the method they want us to use in this question is to solve numerically by plugging in each of these values that are really close to 0 and then seeing what happens. So we'd plug in, for example, e to the power of negative 0.1 minus 1 divided by negative 0.1. So that is 0.95. And then we plug in negative 0.01, which is closer. So you would need your calculator to do this. This is 0.995. The next one is negative 0.001. This is 0.9995. Okay, and I'm gonna stop talking. I'm just gonna write the numbers from now on. Okay, actually there should be one more 9. And then 0 is undefined. So I'm just going to write undefined down here. And then now we plug in all the positive numbers. So 0.0001 is 1.00005. And by this point, it should be clear what the limit is. Because we can basically approximate the value of this limit, looking at what's on the left and what's on the right. This is 1.005, 0.01 is 1.05, and plugging in 0.1, we get 1.05. So basically, if I were to plot our function, I don't know exactly what this function looks like, but if I were to plot it around the points they gave us, so let's say this is, I'll write it in pink. Let's say this is 1. So our function is it's approaching 1, and actually at 1 there's a hole, because the function is undefined, and then it continues to rise. So still, even though the function is undefined, we're looking for the approximate behavior, and we can see that the function approaches 1. So the answer is F. Okay, moving on to question 2. Question 2 asks, which of the following functions has a hole at x equals 5? Alright, so, okay, a hole at x equals 5, so if I were to graph a function, basically, at the point x equals 5, the function is undefined. And usually how this happens is plugging in 5 to the function leaves 0 in the denominator. Okay, so we can basically look at all of the options we're given and see for which one when I plug in 5, do I get a remainder? Do I get 0 in the denominator? So if we look at A, if we plug in 5 for the denominator, we get 5 squared minus 25, so that's equal to 0. So that means A is a possible answer choice. For B, if I plug in 5 in the denominator, I get 10. So that's not correct. And you'll see if I plug in 5 for f of x, that's equal to 5/10. So clearly it's defined because there's a value. Okay, C. If I plug in 5, I get 0 in the denominator. Actually, I get 0 divided by 0. So I changed my mind. I'm actually going to plug it in for everything. So for A, I get 10 over 0. For C, I get 0 over 0. For D, I get 5 over 0. For E, I get 0 over 10. So that's equal to 0, so this is clearly defined. And for F, I get 1 over 0. All right. So, there's two, as we can see, doing that didn't actually reduce our answer choices by a lot. We still have quite a few answer choices. So there's two kinds of undefined behaviors. Yeah. So, we could either have a whole or an asymptote. So I already plotted what a whole looks like. But an asymptote basically means that a function goes in the direction but never approaches that value. So over here, if I plot 1 over x, the left-hand side limit as this function approaches 0 is positive infinity. Oh, this is actually negative 1 over x. So if I plot the limit of this function f of x, we say the limit is positive infinity because as x gets closer and closer to 0 from the left-hand side, it approaches infinity. So, the basic rule that we can remember is that when we have something that's when we plug in our values and we get a constant over 0, that means that there's an asymptote at that point. So, for example, for question A, for answer choice A, we get 10 over 0. That means that at x equals 5, there's actually an asymptote. So A is not the correct answer. Same with D and same with F. So C is the correct answer because we get 0 over 0. And we can see this by factoring the function. So we can see why, basically I want to show why C results in a whole and not an asymptote. So if I factor the numerator, I get x minus 5 divided by x minus 5. And so what happens is that we can cancel out these values only if x minus 5 is not equal to 0. So I can basically say f of x equals x plus 5 for x not equal to 0, and f of x is undefined, basically. Undefined, there's no value for x equals 0. And so what we essentially end up with, I'm going to plot it up here. What we end up with is basically our line, oh, I should have erased this. This is supposed to equal, okay, sorry. So I made a mistake. This should equal positive 5. So f of x is equal to x plus 5 for any x not equal to 5. So if I plot the function in answer choice C, I basically get something that looks almost like a line, except at x equals 5, there's a hole. Yeah. Okay. All right, moving on to the next question. Question 3 says, which statement is true about the discontinuities of f of x? So first, what we can do is we can plot the function that they gave to us in the problem. So, okay. So I have 1 over here, and then I have 3 over here. Okay, so for x less than 1, the f of x is equal to 5x. So, and then notice that there's a less than sign. So for this part of the function, there's a hole. So it's going to look something like this. Okay. And I'm going to change the color. So I'm going to draw this part in pink. Okay. And then for f of x equals, for x in between that is greater than or equal to 1 or less than 3, our function is 20 minus x. So we have a less than or equal to sign on the left-hand side. So if I basically what I can do is I can plug in the boundaries. So if I plug in 1, I get 19. So this point is 119 up here. And then I have 17. So this is it's not to scale, but that's okay. So this point over here is 317. And then for x greater than or equal to 3, our function is 2x squared minus 1. So I do the same thing. I plug in 3 over here. That is equal to 17. So that means that since it's a greater than or equal to sign, this is a filled in point, and it would look something like this. Okay, and they ask us what is true about the discontinuities of f of x. Okay, so we can basically notice two things. So in our function is split into 3 parts. Each of the individual parts themselves are continuous. Like 5 of x is continuous for all values of x. Same with 20 minus x since it's linear, and same with a quadratic 2x squared minus 1. So we don't have to worry about any discontinuities in between the parts. We just have to worry what happens at the edge when we change from one function to the next. So let's consider the change between 20 minus x and 2x squared minus 1. So that is at x equals 3 over here. And we'll notice that there are no problems because when x is equal to 3, the left-hand side limit, if we plug in 3 for 20 minus x, so 20 minus x, we plug in 3, that's equal to 17. And we already plugged it in for the right-hand function. We got 17 as well. So basically, there's no discontinuities over there. And I think that's pretty easy to see graphically as well. But if we look at the other transition, the transition between 5x and 20 minus x, we can see that there's a pretty big gap over here. It's fairly obvious that that function isn't continuous. There's this huge jump between y equals 5 and y equals 19. So that means that the function is discontinuous at x equals 1. Yeah, and an easy mistake here would be to say that a function is discontinuous at x equals 5 or x equals 19 because the y-coordinate is 19 for one function and the y-coordinate is 5 for the other function. But what we are considering is the x-coordinate. So that's why the answer for 3 is C. And if you're having trouble with continuity, a really easy way to think about it is, can I draw my function without picking up my pencil? So if you kind of look over here, if you look at our function, when you get to x equals 1, you need to pick up your function, need to pick up your pen to keep drawing the function. Okay, moving on to question 4. So question 4 says, the graph of f of x is sketched below. Find the limit as x approaches -2 and the limit as x approaches 1 of f of x. Okay, so basically limit means approximate behavior of a function as it approaches a certain value. So usually for a function, if we want to know its value at a certain x, all we have to do is plug in that x. But sometimes we're given functions like f of x equals 1 over x. Well, if I try to plug in 0, I get 1 over 0, which is not, it's not a valid real number. And then we also want to know the behaviors of functions as they approach infinity, negative infinity. You can't just plug in infinity and negative infinity. So that's why we use limits. So in this case, we basically have a two-part question. So let's do the first part. What's the limit as x approaches -2? And this is pretty easy. All we have to do is look at the graph. So let's start maybe at like -2.5. So if I follow the graph, I can see that it goes lower and lower and lower, but it's not touching -2 yet. And so since it's, when we have this kind of behavior where a function goes in a certain direction, but doesn't actually touch the value, so it's getting closer and closer to -2, but it's not actually touching it, that we call that an asymptote. And so basically what's going to happen is that on the left-hand side, so we call this the left-hand side limit. I think we write it like that. So basically, this is going to approach negative infinity. Let's look at the other side, though. So on the other side, we actually start above if we start looking from -1.5, what happens as we approach -2? The graph is actually going upward, and it seems to be doing the same thing, except this time instead of going to negative infinity, it looks like it's going to positive infinity. And so when we have a valid limit, that only occurs when the left-hand side limit and the right-hand side limit are equal. And in this case, our left-hand side limit and right-hand side limit are approaching different values. So when that happens, so I'm going to write LHS limit. When the LHS limit is not equal to the right-hand side limit, we say that the limit does not exist. So for part 1, the limit does not exist. Again, graphically, we can just look at it by think about it as, okay, on the left-hand side, the function is going negative. The right-hand side, it's going positive. So there's no possible way to describe where the function would be at -2, because it can't be positive and negative at the same time. Yeah, it can't go to negative infinity and positive infinity at the same time. It's a better way to think about it. Okay, so that was the first part. Let's look at the second part. The second part asks us for the limit as x approaches 1. So we can do the same thing. If we plugged in the value, what we would get is 2. However, that's not the actual behavior of the function, because there's a hole at 1. Yeah. So what I would do is I would slowly, maybe I'd start around 0.5, and I'd slowly get closer and closer to x equals 1 and see where is the function like taking me. And it looks like it's taking me to y equals 0. Just graphically, like it looks like the function is ending up around y equals 0. And then at the value 0, there's a hole. But we don't really think about holes. And now we do the same thing on the other side. Maybe I'll start around 1.5. And then as I'm going closer and closer and closer to x equals 1, I can see, okay, it looks like it ends up around the point 1, 0. So both the left-hand side and the right-hand side limit are equal to 0. So therefore, we can say that the answer for the second part is 0 as well. So therefore, the answer to question 4 would be A. All right, moving on to the question 5. All right, question 5 asks us to find the derivative of y equals 6 times square root x minus 3 over x squared minus 8 times the fourth root of x to the power of 5. So this looks really intimidating, but all we need to solve this is the power rule. And power rule basically states that the derivative of x to the power of n, assuming n is a constant, is equal to n times x to the power of n minus n. Okay, and n is a constant. Okay, so it at first glance it looks like we don't have any exponents here, but that's because we can actually convert our square roots and our fourth roots to exponents as well. So 6 times root x can be written as 6 times x to the power of 1/2, because taking something to the power of 1/2 is equivalent to taking its square root. Minus 3 over x squared can be rewritten as 3 times x to the power of -2. And 8 times the fourth root of x to the power of 5 can be written as x to the power of 5 to the power of 1/4. And that can be rewritten as x to the power of 5/4. So all of these, everything that I did here translates from basic exponent properties. So if you're not sure where that came from, look up exponent properties and refresh on those maybe. Okay, so now we can take the derivative as normal using the power rule. And when we're taking the derivative of things that are being basically, if I want to find the derivative of this entire thing, I can just take the derivative of each of my individual parts and then and then combine them. So the derivative of 6 times x to the power of 1/2 would be 6 times 1/2 to the power of times x to the power of -1/2. Okay. The derivative of -3 times x to the power of -2 would be 6 times x to the power of -3. And for our last part, the derivative of 8 times x to the power of 5/4 would be 8 times 5/4, which equals 10 times x to the power of 1/4. Okay, and that makes, okay, and so if we see our answer choices don't look like any of these, and none of our answer choices look like what we just got, so we have to use our exponent rules to translate everything back. And the way we do that is we use our exponent rules again. So -1/2 is basically equivalent to saying 1 over x to the power of 1/2, which is equivalent to 1 over the square root of x. 6 times x to the power of negative 3 is essentially 6 over x to the power of 3, and then x to the power of 1/4 is the 4th root of x. Okay, and so that means that our answer to problem 5 is D. Okay, question 6. Question 6 says the position of a particle moving in a straight line is given by s of t equals 7/3 t cubed minus 7t squared minus 56t plus 10. At what time is the particle's velocity 0? So first, they want us to find the moment at which the particle's velocity is 0, which means we need to solve for velocity. The way we do this is we find the derivative of the position vector, or position. We find the derivative of position. So basically, velocity is equal to the derivative of position. So, and this is just a formula that you have to remember. Okay, so if we find to find the derivative of s of t, we can use the power rule, which I'll write up here. Power rule, the derivative of x to the power of n is equal to n times x to the power of n minus n, assuming n is a constant. Okay, so in this case, I would take 7/3 times 3 times t squared minus 7 times 2 times t to the power of 1 minus 56 plus 0. The 10 becomes a 0. Okay, and this is equal to 7t squared minus 14t minus 8. Okay, and I'm going to write v of t, because again, velocity is equal to the derivative of position. Oh, I don't know why I wrote 8 here. This should be a 56. Okay, now they want us to find the time at which the velocity is equal to 0, so we can set all this equal to 0. And you'll notice that the entire left-hand side is divisible by 7, so this becomes t squared minus 2t minus 8. And this is pretty simple to factor, so we get t minus 4 times t plus 2 equals 0. And yeah, that means t equals 4 or negative 2. Negative 2 isn't an option because negative time doesn't exist. Our starting time is t equals 0, so it's also not an option. So our answer to problem 6 is B. Okay, moving on to question 7. Question 7 says we want to find the derivative of f of x equals 1 over 5x using the limit definition. In which of the following is the limit definition set up correctly? So to solve this question, the best, most surefire way would be to just remember and memorize the definition of a derivative, but I'm just going to quickly go over what you would do, say, if you forgot or something. So, let's say I'm going to draw my f of x. Okay, so the definition of a derivative is basically what we do is we assume we have a secant. So a secant is a line that can intersect a graph more than once, and we want to find the slope of this secant. Okay, and what we do is we consider, okay, what happens if I make the distance between these 2 points that I just marked smaller and smaller? So maybe let's say that I move my second marker a little bit over here, and so, oh, that's not very good drawing. Okay, so maybe I move it over here, and then maybe I move it super close. And what basically happens is as I move it closer and closer and closer, the slope of my secant is actually, the secant is going to become tangent to the graph, and the definition of a derivative is actually the slope of the line tangent to your graph. Okay, so maybe I'll write that down. So definition of derivative, slope of the line tangent to f of x. Okay. And obviously the derivative changes depending on the value of x, because your tangent line will change. So, okay. So we can call this point over here x, and this point over here x plus h. And what we want to do is we want to find the slope of the line of this secant. Okay, so slope is always given by delta y over delta x. We take f of x plus h minus f of x divided by the delta x. And the delta x is x plus h minus x. Okay, and what we want to do to find the tangent line, like I said, what we need to do is we need to make h as small as possible. And so how do we mathematically represent something getting small as possible? We use limits. And we say limit as h approaches 0. And so actually what I just solved for, what I'm writing down right now, is the definition of a derivative. So this is the definition of a derivative. Okay, now all we have to do is plug in our function, plug in x and x plus h for 1 over 5x. So f of x plus h is 1 over 5 times x plus h. We subtract 1 over 5x, and we divide by h. So according to what we just solved, that means our answer is F. Alright, moving on to question 8. So question 8 says, find the equation of the tangent line to the graph of y equals 2x cubed minus 3x at x equals 2. Okay, so one thing we know is that the slope of the tangent line to a function f of x is the derivative of f of x. So say if I have a function and I want to find the slope of the tangent line at f of 1, what I would do is I would find the derivative of f of x and then plug in 1 to the derivative. And then that's how I could find the tangent line. So what I'm going to do first is find the derivative. So y prime. The way we do this is with the power rule, which I will write up here. So derivative of x to the power of n is equal to n times x to the power of n minus 1, assuming n is a constant. Okay, so by the power rule, that's equal to 2 times 3 times x squared minus 3 times 1 times x to the power of 0, which is equal to 6x squared minus 3. Okay, the second step, to actually find the value of the tangent line slope, I plug in 1 to y prime. And if I do that, I get 6 minus 3, which equals 3. So 3 is the slope of the tangent line. Okay, the other piece of information we need, so if we have a slope, we either need the y-intercept, like we can either put our line into slope-intercept form or point-slope form. And slope-intercept form obviously doesn't work here because they don't give us any kind of intercept. So we need to use point-slope form. And the way we do that is with the... Oh, I actually made a mistake. I don't know why I plugged in 1. We should plug in 2. because they ask us for the tangent line at x equals 2. So process is still the same. We plug in 2 instead, and I get 24 minus 3, which is 21. Okay. And then now what I need to do is I need to plug in 2 for the original equation so I can find the point at which the line goes through. Yeah, the point at which the tangent line intersects. So if I plug in 2, I get 2 times 2 cubed minus 3 times 2, and that is equal to 16 minus 6, which is 10. So 2, 10 is a point. So if I use slope-intercept form, I get y minus 10 equals 21 times x minus 2, which gives me y equals 21x minus 32. So our answer is F. Alright, moving on to question 9. Question 9 says, given y equals 4x times cosine x, find y prime of pi over 4. Okay, so the first step here is to solve for y prime. And to do this, we are going to need to use the product rule. So the product rule states that the derivative, so let me write it this way, the derivative of u times v is equal to u prime times v plus v prime times u. So, okay, so our two functions here are 4x and cosine x. So we need to find the derivative of 4x and the derivative of cosine x. The derivative of 4x is 4, and so basically I'm going to say that 4x is u and cosine x is v. So the derivative of 4x is 4 by the power rule, and we leave cosine x alone because we just have v. And then now we have v prime u. So u stays the same, so 4x will be 4x still, and we need to find the derivative of cosine x. And we can do this using our basic trig rules, and the derivative of that is negative sine x. That's just something that you have to memorize. Okay, and then last step is plugging in pi over 4. This becomes negative 4x sine of pi over 4. Okay, so I'll tell you the value right now. Okay, yeah. Okay, so the value of cosine pi over 4 is root 2 over 2. So this becomes 2 root 2, and the value of sine pi over 4 is also root 2 root 2, so this becomes negative root 2 over 2 times pi. Yeah, and so if you have your trig values memorized, that's awesome, so it's really easy to do. But if you don't, what you can do is you can draw out the unit circle, and pi over 4 is basically right over here, and that's where x and y are equal to each other. So basically you could either use 45, 45, 90 triangles, so this angle is 45 degrees. You could either use 45, 45, 90, or Pythagoras theorem to solve for the trig values. And I personally would use Pythagorean theorem because according to the unit circle, the hypotenuse is 1, and since both angles are 45 and 45, they're equal to each other. So I know that by the Pythagorean theorem, 2x squared is equal to 1, which means x is equal to root 2 over 2. And sine is equal to the x value divided by the hypotenuse. Sine is equal to the y value divided by the hypotenuse. Cosine is equal to the x value divided by the hypotenuse. So it doesn't make a difference either way. That's how you can determine that sine of pi over 4 or cosine pi over 4 equals root 2 over 2. Then you plug things in, and that's how you get that the answer is B. Okay. Alright, question 10 says, given f of x equals 3 times e to the power of x minus 1 divided by 3 times e to the power of x plus 1, find f prime of 0. Okay, so what we need to use for this problem is the quotient rule. Quotient rule states that the derivative of u divided by v is equal to u prime v minus v prime u divided by v squared. Okay. So all we have to do is basically find u prime, find v, and then plug things in. Okay, yeah. So we know u is equal to 3 times e to the power of x minus 1, and v is equal to 3 times e to the power of x plus 1. That makes u prime equal to 3 times e to the power of x. This is because the derivative of e to the power of x is e to the power of x itself. So when I take the derivative, nothing changed with 3 times e to the power of x because our multiplying constants stay the same, and our constant minus 1 disappears due to the power rule. Actually, no, not due to the power rule. It just disappears because it's a constant. And then v prime also becomes 3 times e to the power of x for the same reasons. Okay, now all I have to do is plug things in. Okay, the way I wrote this is not very good, so basically d dx of u over v is equal to what I wrote over here. Okay, if I plug things in, I get 3e to the x times 3e to the x plus 1 minus 3e to the x times 3e to the x minus 1 divided by 3e to the x plus 1 squared. Okay, I don't have to expand any of this out because they tell us they want to find f prime at 0. So I can just plug in 0 right now. That's really good for us because e to the power of 0 is just 1. So that's going to make things really easy for us to solve. Okay, so this becomes 3 times 3 plus 1 minus 3 times 3 minus 1, which is 2, divided by 3 plus 1 squared, which is 4 squared. So 12 minus 6 is 6 divided by 16, which is equal to, it's equal to 3/8, which means the answer to 10 is A. Alright, moving on to question 11. Okay, question 11 says, if h of x equals tangent x and cosine x, what is, tangent x minus cotangent x, then what is h prime of x? Okay, so there's no shortcut for this. The only thing, all you need to do is just memorize your trig derivatives. That's the best way to do it. So the derivative of tangent x equals secant squared x. Okay. and the derivative of cotangent x equals negative cosecant squared x. So that means that h prime of x, I'll write it a little below. Okay, h prime of x equals secant squared x minus cosecant squared x. And that means that the answer to question 11, oh, you have to be careful, it's actually equal to secant squared x minus cosine squared x. So that could have been a really silly mistake to make, but the answer is equal to secant squared x plus cosecant squared x, which is A. One way I do like to simplify the things I'm like remembering. So you have to memorize all your trig derivatives, of course. But the way I memorize like cotangent and cosecant is first I make sure like I memorize tangent. So basically tangent of x is equal to secant squared x. Secant x equals secant x times tangent x. So I make sure to always remember these. And then in order to get cotangent x, all I have to do is I have to switch secant to cosecant and tangent to cotangent and add a negative sign. So secant, I add a negative sign and make it cosecant x squared. For cosecant, I do the same thing. I switch the secant to a cosecant. I switch a tangent to a cotangent, and I add a negative sign. Yeah, and I mean, it's not it doesn't save your memory space a lot, but it's a helpful trick for memorizing all of the different trig functions. Okay, moving on to question 12. Question 12 says find g prime of 1. So, g of x is equal to negative x divided by x squared minus 2 to the power of 3. And so what's unique here is that we have multiple functions that are nested inside each other. And so when we have something like that, we use the chain rule, which states that the derivative of f of g of x is equal to f prime of g of x times g prime of x. So basically, it's kind of like we're unwrapping a present, except the present is our functions. So we take the derivative of the outside stuff, and then we multiply by the derivative of the inside stuff. Yeah, basically. So what I would do here when finding the derivative of g prime of x, we see that our main function on the very outermost function is all of this stuff to the power of 3. So we just use the power rule. This is the first part of our chain rule. And now we want to find the derivative of negative x divided by x squared minus 2. Okay? And so to find the derivative of the second part, what we need to use is the quotient rule. Which states that the derivative of u over v equals u prime times v minus v prime times u divided by v squared. Yeah, so that's what we have in our problem essentially. U is negative x and v is x squared minus 2. So or maybe on the side, if I solve for u prime, the derivative of negative x is simply negative 1 by the power rule, and v prime, the derivative is 2x. It's 2 times x to the power of 1. So now I can just plug those values in. I'm going to take this down here, so I get in the denominator, I just have x squared minus 2 squared. The numerator, I have u prime times v, so negative 1 times x squared minus 2 minus v prime, which is 2x, times negative x. Okay, and now if I plug in 1, what I get is I get 3 times negative 1 divided by negative 1 squared times negative 1 times 1 minus 2 minus 2 times negative 1 divided by negative 1 squared. Okay, that's a lot of negative 1s and 1s. And I think if we multiply, if we like do all the math, this becomes 3 times 1 minus negative 2, which becomes 3, divided by 1, which equals 9. And yes, that is the correct answer. The answer to 12 is B.